Okay, this is the first video on inverse trig functions. So one thing, and let's work with sine and cosine first. One thing that you will remember about a function having an inverse, in order to have an inverse, it means that every x value must go to a unique y value. Which means if graphically looking at the function, it should pass, to be a function, it has to pass the vertical line test. But to be invertible or one-to-one, it has to pass the horizontal line test. So if we look at both of these graphs right now, the first one being sine of x and the second one being cosine of x, clearly they're failing at that. So neither passes the horizontal line test. However, there is a way to make functions invertible by restricting the domain. So you always want to restrict the domain such that you're still capturing all the possible y values. And so a few criteria. You want to capture all the y values. You want to make sure that the restricted domain is indeed one-to-one and passes that horizontal line test. And for trig, we also want to make sure that we are capturing acute angles and an interval that's consecutive. So we wouldn't want to capture a group of angles and then say in one interval, like say 0 to pi over 2, and say, okay, more than a period away, that's our other interval. So you really want consecutive intervals here. So a logical one for sine that meets the criteria, again, I'm going to repeat it. First one is it's got to be one-to-one. Second, it has to capture all the possible y values. So in this case, everything from -1 to 1. And you want to include the acute angles. So here, the best, and what was decided to be the best interval to restrict the domain is from -pi/2 to pi/2. So we're looking literally just at this bit here. So when we talk about inverse trig, when we say y equals inverse sine of x, now remember, let's go back a little bit to actually y equals sine of x, because I want to remind you for y equals sine of x, the inputs are the angles. So the domain in this case, when it isn't restricted, is all real numbers. And the outputs are the ratios. And the range, therefore, for sine of x was -1 to 1. Now, remember, when we do the inverse, we flip the domain and range. So in this case, for inverse sine, our new domain is still going to be -1 to 1, which was the range of the original function. However, our range is going to be our restricted domain. So remember what we just had to restrict it to. We had to restrict it to all angles between -pi/2 and pi/2. Well, what does this mean? Well, it means that when you are evaluating an inverse trig function, if the ratio is positive, you're going to answer a quadrant 1 angle. And if the ratio is negative, you're going to give me a negative quadrant 4 angle. And we'll do some examples in a little bit. So again, we just went over the domain and range of the original trig function, and now the domain and range of inverse trig. And we had to restrict the domain of the original function in order to do so. And then just to be complete here, the inputs of inverse trig are the ratios, and the outputs are the angles. So because inverse sine is indeed a function, there always should be only one answer. You won't give me multiple answers. And the one more thing about notation, and maybe some of you have seen it if you've seen standardized tests or ever kind of worked ahead in some sort of workbook, inverse sine is often represented also as arc sine x. So they mean the exact same thing. So when you see arc sine x, that means the exact same thing as inverse sine x. Okay, so that was sine. Now let's talk about cosine. So looking at cosine graph, negative pi over 2 to pi over 2 as our restricted domain, that's not going to cut it, because you can see from negative pi over 2 to pi over 2, you can see here that this indeed is not one-to-one. So again, we want to keep positive acute angles, and we want to have one consecutive interval. So instead of negative pi over 2 to pi over 2, what will work for cosine is using 0 to pi. So this is going to be our restricted interval. So again, it's capturing both all the possible ratios from negative 1 to 1, has the acute angles, and this captures the positive acute angles rather, and it's a consecutive interval. Okay, so let's go back to the original cosine function. So originally cosine, the input were the angles, and so the domain was everything, and the range were the ratios. So now for inverse cosine, or arc cosine, the domain is the ratios, so negative 1 to 1, just like inverse sine. But the range here is our restricted domain of the original, so 0 to pi. So therefore, if you're doing inverse cosine of a positive ratio, you're going to get a quadrant 1 angle. If you're doing inverse cosine of a negative ratio, you're going to get a quadrant 2 angle. Okay, let's go on to tangent. So tangent here, let's looking at it's actually pretty obvious looking at tangent what will be a good interval, and that would be going from negative pi over 2 to pi over 2. It's actually the nice period here that works out well. It satisfies getting the positive acute, all the ratios, and consecutive interval. It's 1 to 1. So let's, like we did with the others, go through all the domains and ranges. So for tangent, the regular tangent of x function, the domain was all reals except every pi over 2 plus k pi, and the range was everything. Now for inverse tan or arc tan, we are restricting the domain to be negative pi over 2 to pi over 2. Oh, sorry. We are restricting the domain of the original, but that's going to be the range of the inverse. Sorry about that. Remember, the domain of inverse is the ratios, so the domain in this case is everything. I can input anything into inverse tan. It's the range that is going to be the new restricted domain of the regular tangent function. So it's going to be negative pi over 2 to pi over 2. And notice I have parentheses here because it doesn't include negative pi over 2 to pi over 2 because that's where tangent is actually undefined. So you would never give that as an answer. Now let's just go through a couple examples, and then in the next video I'll talk about the reciprocal functions and their domain, the inverse reciprocal functions and their domains and ranges. So what if I said, let's do a few breezy ones and then I want to show a comparison. What about, let's evaluate. So the first example, if I said find the inverse sine of negative 1/2, and then for number 2, we'll say find, not sine, find the inverse cosine. Let's do negative 1/2 as well, why not? Let's do inverse tangent of root 3. And let's do inverse tangent of negative root 3. Okay, inverse sine of negative 1/2. The first thing you ask yourself is, what's the reference angle here? Sine of what angle gives me a 1/2? And the reference angle would be pi over 6. Now, since the ratio is negative 1/2, I need to give an angle, an answer in the interval negative pi over 2 to pi over 2. So since the ratio is negative, I'm going to give a negative quadrant 4 angle. I'm going to give negative pi over 6. Now, it is not acceptable to give 11 pi over 6. Even though that's a quadrant 4 angle, that is not between negative 90 and 90 degrees. Or between negative pi over 2 and pi over 2 in radians. You have to give the negative acute quadrant 4 angle. Okay, how about inverse cosine of negative 1/2? Well, for inverse cosine, the range is 0 to pi. So if I have a negative ratio, I'm going to give a quadrant 2 angle. So I'm going to say 2 pi over 3. The reference angle is pi over 3. Positive ones are easy because the answer is always a quadrant 1 angle. So for inverse tangent, it's pi over 3. And for inverse tan, remember, it's parentheses, not equality. It's either a negative quadrant 4 or a positive quadrant 1. So if the ratio is negative, it's going to be negative pi over 3. Okay, more to come in the next video.